Hello dear students, I welcome you all to the last exercise on set theory class 11 mathematics. So with the assumption that we have understood the algebra of sets, let's begin with the today's exercise. So the first question says state whether the following statements are true or false. Okay, so the number one is your idempotent law, isn't it? So since this is directly given as idempotent, that is A union A will always be equals to A, this is always true. All right, now the next is A intersection A equals to phi. Now this is against your idempotent law, because idempotent law says that this will be again A, isn't it? So that's why this will be false. Okay, so A union with its complement will give you universal set. This is always true, isn't it? So this is true. So again, there's a property about this particular question, that is question number 4. So if you go to the algebra of sets, from there you see that this is also true. All right, second one is also true, that is fifth one is also true. Now A intersection with empty set, that means the common elements between empty set and A will be equals to A. Is this true? No, this is always false. All right, now when you take the union of any set with empty set, you'll get back the same set. So this is always true. All right, now the next question is question number 2, which says fill in the following blanks. All right, so you will try this by yourself. So pause the video and note it down. Now let's have a look at question number 3. So question number 3 says show that A intersection B is equals to A intersection C need not imply B equals to C. So basically here questions asking you to give some example where we have A intersection B and A intersection C will be equal, but B equals to C will not be possible. All right, so basically we need to form example out here, as you are going to disprove, right? So whenever you take or whenever you disprove anything, you have to search for some example, and we call it counter example. All right, so let's see. So I'm taking A to be this set, let me take B. So B I'm taking to be this set, and I'm taking C to be this set. Now let's find what is A intersection B. All right, so let us see what is A intersection B. So in between A and B, the only common element that we see here is 3, isn't it? Now we need to find what is A intersection C as well, isn't it? So the common element between A and C is again 3. So we clearly see that A intersection B and A intersection C both are equal. Yes, but we see that B and C, they are not equal, isn't it? See, we have got 3, 4, 5, but here we have got 3, 6, 7. So here we have successfully shown that A intersection B equals to A intersection C need not imply B equals to C. All right, now the next question is also similar. Here also you need to find the sets as we have found in this way. For example, A equals to 1, 2, 3, B equals to 3, 4, 5, and C equals to 3, 6, 7. Now we have written in this way. Similarly, you have to find same thing out here. You have to find set A, B and C says that A intersection B should not be empty, okay, because they are non-empty. That's what the question is saying. Similarly, A intersection C should not be non-empty, B intersection C should not be non-empty. But if you take the common element between A, B and C, there is no common element between them. That is, it will always be equals to phi, that's empty set. So you will try this by yourself. All right, pause the video and note it down. All right, now the next question says let A, B and C be any sets. By drawing Venn diagram, verify this. So this is your distributive property, right? So we have seen how to prove distributive property in the last video, but this time we'll see or we'll verify this using Venn diagram. All right, so let me first draw Venn diagram for left hand side. Now whenever you draw Venn diagram, first you need to draw Venn diagram for the ones which are within bracket. as the board master rule says that we always need to work with the bracket in the beginning, right? So in the left hand side we have got this. All right, so we have got 3 sets. So let me draw 3 sets out here. Now within bracket we have got B union C, isn't it? So if I have to plot B union C here, then your B union C will be this one, isn't it? Now we have drawn B union C out here. Now let's see what is the common element of this B union C with A. All right, so with A, the common element of B union C, that is this yellow part, is how much? Only this one, isn't it? That is this one. So this is the only common part. So this is the Venn diagram of your left hand side. Okay, let's see what is the Venn diagram of right hand side. Okay, so we have A, B and C. First and foremost, let me draw A, B and C. Now within bracket we have got A intersection B. So within A and B, let us see what are the things common. So we see that only this part, this yellow part is common between A and B. So this is your A intersection B. Now we have got another, that is A intersection C. So this is your A intersection C, isn't it? Now you are taking union, that means you are combining the common part between A and B and A and C. So if you combine this and this, you will get this, isn't it? Now see here, this is your Venn diagram for right hand side. Now are they same? Yes, so we have shaded the same part, isn't it? So that's why we have verified distributive property using Venn diagram. All right, so hence using Venn diagram we have this one. All right, so you may pause the video and note it down. So let's see the last question for the day. So question says, show that the following 4 conditions are equivalent. So there are 4 conditions given to you and you need to prove that these are equivalent. Now what's the meaning of this? Let's try to understand. All right, so equivalent means you have to show biconditional statement out here. All right, so that means this implies this and this also implies this. All right, so this is the first thing that we need to prove. Next thing that we need to prove here is this implies this. All right, that is 1 implies 3 and 3 implies 1. That's what we need to show. Okay, so this is our second condition. Now what is left? We have been left with condition number 4, isn't it? So we have this implies 4 and 4 implies 1. So if we are able to show these 3, or if we are able to prove these 3 conditions, then we are done with the problem out here. All right, and in fact we have already seen all these proofs in the last video. So that's why you'll refer algebra of sets, and you will refer property number 12 and 13 for the proofs. All right, so pause the video and note it down. Thank you very much.